Welcome to the deep dive, where we take the source materials you provide and really dig into them to extract the fascinating knowledge inside.
hmm
Today, we're looking up setting our sights on the stars. Specifically, we're diving into why astronomers put, well, so much effort into measuring their positions with just incredible accuracy.
Yeah, it's a great question. You sent us this document, Perryman Gaia 002.pdf, and it really does make you think.
It does, because, your first thought might be, well, stars look pretty fixed up there, right?
Right. I mean, sure, they move across the sky during the night, but that's obviously just us, our planet spinning and orbiting the sun.
Exactly. So the real puzzle is why go to these extraordinary, almost um, unbelievable lengths to measure something that, to the naked eye just seems constant.
That's the hook, isn't it? Why measure something that seems so still? And the answers, well, they unlock some really fundamental things about the universe.
Yeah, we're talking about figuring out the structure of our own galaxy, the Milky Way, even the origin and age of the universe, and the basic physics of stars themselves.
Okay, so let's start there with that illusion of stillness.
Hmm.
You look up maybe over years, decades even, and the constellations, they look the same. But the reality is every single star is moving.
Drifting through space, sometimes pretty fast too, relatively speaking.
Exactly, at significant speeds. And what's interesting is people didn't always know this. It wasn't really nailed down until, what, the early 18th century? About 300 years ago.
Right, 1718. That was Edmund Halley, wasn't it? He showed the first real proof that some stars had actually shifted position compared to ancient charts.
Spot on. That was basically the birth of studying stellar movements. It showed the heavens weren't static, they were dynamic.
Which brings us to this term, proper motion.
Yes, proper motion. The document explains it as the change in a star's angular position on the sky over time, as we see it from here, from the solar system.
Angular position. So, like, how many degrees or fractions of a degree it shifts sideways in our view each year?
Precisely. The name proper probably comes from the French for its own motion, distinct from apparent motion caused by Earth moving.
Ah, okay. So it filters out our planet's wobbles and focuses on the star's actual drift across our line of sight.
Exactly. It's tracking the star's individual journey through the galaxy. Tiny movements, usually, but real.
But, and this is a key thing the document stresses, that angular shift, that proper motion, it's not the star's true speed through space.
No, absolutely not. That's a crucial distinction. It's just the sideways part of its motion as we see it. Think about two cars driving across your field of vision way down the road.
Okay.
If they seem to cross your view at the same speed, but one is much further away,
Then the further one must be going much faster in reality, right? To cover
Mhm.
the same angle in the same time.
Exactly that. Same with stars. A nearby star moving slowly could have the same proper motion as a very distant star that's absolutely rocketing through space.
Gotcha. So to get the real speed, the true velocity, you absolutely need to know.
The distance. Distance is the key.
Which makes sense why, as the document notes, looking for stars with high proper motion, the ones that seem to move faster across the sky, is a decent trick for spotting potentially nearby stars.
It is a useful technique because a nearby star doesn't have to be moving that incredibly fast in actual kilometers per second to show a larger angular shift from our perspective.
But most stars are just so incredibly far away.
Oh, immensely far. So their proper motions are usually tiny, minuscule, even measured over decades. You need incredibly precise measurements.
And this brings us back to why knowing the distance is just so fundamental, not just for speed.
Right. There's another huge reason. Knowing the distance lets you convert how bright a star looks to us, its apparent brightness, into how bright it actually is, its intrinsic luminosity.
Ah, so like
Yeah,
knowing if a dim light bulb is dim because it's low wattage or just because it's really far away?
exactly. Intrinsic luminosity is a core physical property of the star.
Hmm.
It tells you how much energy it's actually pumping out.
And that unlocks all sorts of other things.
Everything. It's the key to understanding its composition, what nuclear reactions are happening inside, its temperature, its size, its mass, its age, how it's going to evolve. Basically, the star's entire life story in nature. Without distance, you can't get that true luminosity, and you're missing a massive piece of the puzzle.
But these distances, I mean, the document really tries to hammer home just how vast they are. The analogies are almost dizzying.
They really are. John Herschel's image, needing a fleet of 10,000 ships just to put 1 p every mile to reach the nearest star. It's hard to picture.
Or spacing out every single person on Earth just to cover the distance to Proxima Centauri.
Yeah, it highlights the sheer emptiness, doesn't it? That scale model is great too. Sun as a 1 centimeter marble, Earth a grain of salt a meter away,
Pluto at 40 meters.
and the nearest other stars
Yeah.
200 kilometers away in that model. Just staggering emptiness.
So, okay, the distances are insane. How on Earth, or rather, how from Earth do we measure them? This is where parallax comes in.
Yes, parallax is basically triangulation, like surveyors use. But on a cosmic scale, the key idea, which Copernicus helped us realize, is that Earth orbits the Sun.
So we're constantly changing our viewpoint throughout the year.
Exactly. As Earth moves from one side of its orbit to the other, say 6 months apart, our vantage point shifts by about 300 million kilometers.
And from these slightly different viewpoints, a nearby star will seem to shift its position.
Precisely. It appears to move back and forth slightly against the backdrop of much, much more distant stars, which seem fixed because they're so far away.
Like the classic experiment. Hold your finger out, close one eye, then the other. Your finger jumps against the background.
That's exactly the principle. That apparent yearly wobble of a nearby star against the distant background. That's stellar parallax.
And the amount it seems to shift by, that's the parallax angle.
That's the one. But again, because the distances are so vast, this angle is incredibly, incredibly small.
Like the documents analogy. Trying to measure something 200 kilometers away by moving your viewpoint the width of a grain of salt orbiting a marble.
Yeah, it captures the challenge perfectly. We're talking about angles so small they're hard to even describe. Imagine trying to see the width of a human hair from over a kilometer away.
Wow. Okay. No wonder it took astronomers centuries of trying before they could actually measure it. The first success wasn't until the 1830s.
That's right. Bessel, Struve, Henderson around that time. Before that, the inability to measure parallax was actually used as an argument against the idea that the Earth moved.
Because the angles were just too small for their instruments. Incredible.
Absolutely. And even for the closest stars, like Proxima Centauri or Alpha Centauri, the parallax angle is only about 1 arcsecond.
An arcsecond. Remind us how small that is.
Okay, imagine a circle divided into 360 degrees. Each degree is 60 arc minutes. Each arc minute is 60 arcseconds. So 1 arcsecond is 1/13/600th of a degree.
Tiny. Like looking at a coin from several kilometers away.
Pretty much. And for stars further away, the parallax angle gets even smaller fractions of an arcsecond. It's also kind of an unfortunate coincidence that the blurring effect of Earth's atmosphere is often around 1 arcsecond too.
So from the ground, the star's image was basically blurred by about the same amount it was expected to wobble, for nearby stars at least, making it super hard to measure.
Exactly. That's why pushing measurements down to milliarcseconds, thousandths of an arcsecond, was such a huge challenge, and why going into space above the atmosphere was revolutionary for this kind of work, like the Hipparcos satellite and now Gaia.
Game changers. And this fundamental measurement, the parallax angle, it's so important it defines the main unit of distance, right? The parsec.
It does. It's baked right into the name. A star is at a distance of 1 parsec if its parallax angle is 1 arcsecond.
Parallax second, parsec. Got it. That was officially adopted when? 1922.
Around then, yes.
Yeah.
It became the standard professional unit because it relates directly to the measured angle.
We also hear about light years all the time. How does that fit in?
Light years are another perfectly valid way to talk about these distances, maybe more intuitive for the public sometimes. It's the distance light travels in 1 year. 1 parsec works out to be about 3.26 light years.
And a light year is huge.
Oh yeah. About 10 trillion kilometers or 6 trillion miles. So the nearest stars, Proxima and Alpha Centauri, are just over 1 parsec away, or about 4 light years. Still an unimaginable distance.
And the document gives some great scale examples. The Hydes cluster, maybe 40-odd parsecs away.
Yep, a nearby cluster. Then the spiral arms near us, maybe 500 parsecs. The center of our galaxy, nearly 10,000 parsecs. That's like 30,000 light years.
That's right. And the Magellanic Clouds, those companion galaxies to the Milky Way, around 50,000 parsecs. We start getting into kiloparsecs, thousands of parsecs.
And big galaxy clusters are millions, even tens of millions of parsecs away. Megaparsecs. The scale just keeps expanding.
It really does. So let's pull it together. What we see for any given star is a combination of 2 tiny motions.
Okay. One is its own slow drift across the sky over years, the proper motion, right? Due to its actual velocity through space relative to us. And the other.
That tiny yearly back and forth wiggle caused by us looking at it from different points in Earth's orbit, the parallax.
Exactly. Proper motion tells us about its sideways velocity. once we know the distance, and parallax gives us the
Oh,
distance.
yes. And now, with modern instruments, especially space telescopes like Gaia, we can measure these angles so precisely.
Down to microarc seconds in some
And
cases.
we can start to detect even subtler effects overlaid on top of those two main motions.
That's where cutting-edge astrometry is now. You can measure the tiny wobble a star makes because it's in a binary system, tugged by an unseen companion.
Or even smaller wobbles caused by orbiting planets pulling on the star.
Yes, that's one of the ways exoplanets are found or confirmed. And even things predicted by Einstein's general relativity, like the slight bending of starlight as it passes near another massive object.
Wow. So measuring position isn't just about location, location, location. It's about gravity, planets, fundamental physics.
It all comes out in the wash once your measurements are precise enough. These are the frontiers.
So for you, the listener, we hope this deep dive has sort of shed some light on why astronomers are so obsessed with pinning down star positions. That question we started with, why bother measuring these seemingly fixed points?
Well, the answer is it's the key. Measuring proper motion and parallax gives us distance. Distance turns apparent brightness into true luminosity, and that unlocks the secrets of the stars themselves, their physics, their lives, their evolution.
And it doesn't stop there. Knowing distances and motions helps us map out the structure of our entire Milky Way galaxy, how it rotates, how it formed. It underpins basically all of astrophysics beyond the solar system.
It really does. It's amazing to think about that journey. From people looking up thousands of years ago, seeing unchanging patterns, to Halley realizing, wait, they do move, to the struggles to measure parallax, and now measuring positions with enough accuracy to see planets orbiting other stars hundreds of light years away.
It really makes you wonder, doesn't it? As these techniques get even more precise, what else are we going to find encoded in those tiny shifts and wobbles? What new layers of the cosmic story will be revealed?
That's the exciting part. The ongoing work, the next generation of instruments,
Yeah.
they'll continue to refine our picture of the universe, maybe in ways we can't even anticipate right now. It's
Yeah.
something definitely worth thinking about.